Tonight's video lesson is over conversion factors and dimensional analysis for chemistry. This is video lesson 2 for our unit on battery power. My objectives for you tonight are that you'll be able to convert between grams and moles, you will be able to convert between liters and moles, and you will also be able to convert between atoms or molecules and moles. We are going to be using dimensional analysis a lot for the rest of the trimester here, so I'm also going to teach you the basics of dimensional analysis. Before we get into the dimensional analysis portion of the lesson tonight, I'm going to go over real quick what a mole is. And a mole is equal to 6.02 times 10 to the 23rd representative particles. Okay. This unit of measurement is similar to that like a dozen bagels or a dozen eggs. The dozen just tells you how many. You can change whatever that dozen is measuring. With a mole, this is saying, like, if I was talking about dollar bills, if I had a mole of dollar bills, this would be 6.02 times 10 to the 23rd dollar bills. Or if I had a mole worth of bagels, that would be 6.02 times 10 to the 23rd bagels. It's a very large unit to measure something that's very small. When you're measuring atoms or molecules, you're not dealing with just a dozen or 10 or 100. You're dealing with a very large amount of these in a small space. Before we get too far into stoichiometry, we need to learn how to do dimensional analysis and some simple conversions. And what dimensional analysis is a way to organize conversions between multiple units. And what you do for this is you multiply across the top and you divide across the bottom. And you'll be able to track the units that you're canceling out as you go along. In order to do dimensional analysis, though, you need to use conversion factors that you know. And so, for example here, if I wanted to convert between 2.76 hours and I wanted to know what this was in minutes, okay, I could set this up in a way that I can use a conversion factors that I know in order to determine this. And so when you do dimensional analysis, you always start by writing down what you know to begin with. And we're going to end with what we're trying to find. So I'm starting with 2.76 hours. Okay. And then the vertical line here is going to indicate the separation of my next step here. And so I need a conversion factor for this to work to go from hours to minutes. And so for my conversion factors, I know that in 1 hour there are 60 minutes. And like I said before, when you do dimensional analysis, we're going to multiply across the top and divide across the bottom. Now, when I'm checking to see if my units are correct here, if I look at the diagonals here, I can see that I've got hours here in my initial answer, and I've got hours here on the diagonal to it. And so what that leaves me with at the end here, after canceling out my units, is I'm left with minutes. Now when I do the math for this, I'm going to do 2.76 times 60 and divide by 1. When I do this, this answer comes out to 165.6 minutes. Now this here is referred to as a single step conversion because you're converting from the unit that you began with into the unit that you're going to end the answer with. And we probably can already do this without using dimensional analysis. Dimensional analysis is more useful when we're going multiple steps here to keep track. So if I take, for example, my 2.76 hours again, and I want to convert it to seconds. I'm going to start with what I know, which is 2.76 hours. I always include my unit. And so for that first step still it's going to be 1 hour, and that there's 60 minutes. Now, I'm still not in the unit that I want to have my final answer. I'm looking to be in seconds. So I'm going to have to do a second conversion here where I go from a known conversion, which is that 1 minute has 60 seconds. When I cancel out my units here now, hours cancels out and minutes cancels out. This should leave me with just seconds in my final answer. And if I go and calculate this, this is equal to 9,936 seconds. When I multiply 2.76 times 60 minutes times 60 seconds, and I divide by 1 hour and divide by 1 minute. The use of dimensional analysis will come in handy when we get into stoichiometry, but let's use an example here where we're using something that we would experience in chemistry. One thing that you will be asked to do is to be able to convert between grams and moles. And so if I had an example here where I wanted to go from 27.26 grams of carbon, and I wanted to convert that into moles here. The conversion here, just like before, I'm going to start with what I know, which is that I have 27.26 grams of carbon. Now for my conversion of going from grams to moles, you're going to use the atomic mass that's listed in the periodic table to go from grams to moles. And so the atomic mass for carbon is that there are 12.001 grams of carbon in 1 mole of carbon. And just like before, I cancel out on the diagonal here, and then I'll multiply across the top and divide across the bottom, so 27.26 times 1 divided by 12.011 gives me an answer of 2.27 moles carbon. If I wanted to convert from moles to grams, I would take my starting answer or starting point of moles, and in 1 mole the atomic mass of what I'm trying to find. Okay, and that would give me my answer in grams. You're just going to invert your conversion factor from going from grams to moles to grams instead. We can also use the mole to convert from atoms to moles here. If I were to look at 7.25 times 10 to the 25 atoms of aluminum, I'd have to use the conversion factor that we know that moles represent in this case. And so from before, a mole represents 6.02 times 10 to the 23rd atoms of aluminum, and that's equal to 1 mole. So when I do 7.25 times 10 to the 25 atoms of aluminum and divide that by 6.02 times 10 to the 23rd atoms of aluminum, I get a final answer of 120.4 moles of aluminum. My last conversion factor that I'm going to do tonight is converting between liters and moles. And so 22.4 liters is equal to 1 mole. So if I have a question where I start with 35.27 liters of oxygen gas, and I want to know how many moles this is, I would start with 35.27 liters of O2, and then I would put my conversion factor to go from liters to moles. So 22.4 would go on the bottom because that's what I'm converting from. This is what I'm going to cancel out. And 1 mole of O2 would go on top because that's what I'm trying to figure out. When I do my canceling here, liters are on diagonal of each other, so I've set this up right, so my final answer should be in moles. 35.27 divided by 22.4 gives me an answer of 1.57 moles of O2. What we're going to use dimensional analysis for over the next couple weeks here is I'm going to be giving you some labs where I tell you the starting amount that you're going to be given for the reactant. So we're still going to be using chemical reaction types. And I'm going to ask you to determine what mass or what volume or how many atoms of a product that you should produce at the end. This is stoichiometry and it uses dimensional analysis. So we'll be looking at this a lot over the next couple weeks. Be prepared to do some math here, and just remember that you need to have conversion factors to use dimensional analysis.